Spirometer and Board of Advisors. We are Team 8, second ranked, and we're here to bring you the Incentive Spirometer 2.0. The Incentive Spirometer, we seek to modernize it, and not only that, but add an additional OPEP function to the device. OPEP standing for Oscillating Positive Expiratory Pressure. Part of the team, Jason Smith, mechanical engineer. Here we have
Mohammed Day, electrical engineer.
And I'm Sehu Joe, the computer engineer.
Nate Geller, mechanical engineer. Omar Gurbe, mechanical engineer.
Due to anesthetics and different surgeries, one's alveoli can become depressed and need rehabilitation. And in order to rehab, doctors usually prescribe spirometers. But a big problem with spirometers nowadays is people don't fully complete the rehab given to them by their doctors. The use of, while partnering with Lung Technologies and Northwest Orthopedics in Spokane, we will create a new and improved and incentivized spirometer that will allow the user to be more engaged and want to use it to complete the rehab, and also give a function for the doctors to be able to get their information in real time without the lying of the user. And this is what a spirometer looks like. Here you'll breathe into the mouthpiece, which will make the piston rise, and what we are planning on incorporating is an electrical system that will be able to get the output of the spirometer and see if it's successful or not. And the way that we plan on doing so is by aesthetically redesigning the spirometer with the addition of our electrical system. We also plan on adding an OPEP device by the mouthpiece area, which will allow us to help with exhalation therapy. And we'll also create a self-regulating valve system that will be able to tell whether or not we are performing inhalation or exhalation, because we have different therapy uses for those. The different risks that we have a lot of risks actually that we plan to prevent, and the ways that we plan to prevent this is by using the spirometers that are already on the market now, because these have already been tested out and are very accurate. And we also plan on building and testing our electrical components and making sure that they're detachable and usable. And the way that we plan on doing this is by simulating airflow in SolidWorks in the diaphragm of the spirometer, and also by testing the loads of the different components in our electrical system through the use of multisync.
In our research with the problem space, we found out that medical devices are expensive. So the Incentive Spirometer 2.0 will save cost. And the way we're going to do it is the electronic device that we are designing will be attached to the spirometer, but you can also detach it from the spirometer and use it across maybe 10 different other spirometers, and this can help spread costs across those spirometers. Pulmonologists also require reliable information from patients, because sometimes when patients are told or given a prescription to do a lung exercise, let's say 10 times, most of the time, according to research and pulmonologists, patients lie about how many times they've done their lung exercises. So we are trying to remove the patient out of the equation by designing this electronic device that will be attached to the spirometer that will record the inhalation level of patients. That way, the doctors and pulmonologists have reliable data to better mitigate patients' well-being. We're also integrating an OPEP device with the spirometer, and this will have space inside the ICU, because the ICU or the patient rooms are really tight on space. So integrating the OPEP device with the spirometer will have save space.
All right, for our block diagram, we broke it into two components, the mechanical and electrical components. I'll be talking about the mechanical components, while Makana will be talking about the electrical components. So, for the mechanical aspects, we have the patient breathing in through the mouthpiece and tube. Their airflow will then go into the valves, which connect to the diaphragm and ideal flow indicator. The diaphragm has a piston in it, which rises as the patient breathes in. This will indicate the patient's volume of their breath. The ideal flow indicator will move as the patient is breathing in, indicating their flow rate. This all adds into the electrical components, which Makana will now talk about.
Well, as the diaphragm raises, we will need to be able to measure whether or not that diaphragm has reached the certain volume that was prescribed by the doctors. And the way that we plan on doing that is by some sort of sensor, which you see right here, which will sense if the diaphragm has reached that point. In order to collect this data and tell the user whether or not tell the user and the doctors whether they've reached that expected level of volume, we have a microcontroller connected to a memory bank. And this microcontroller will be able to tell the user on an LCD screen whether or not they've reached that indicated level of volume that they need to by the doctors. And it will also be connected to a timer and speaker, which will have two functions. The first function will be to also tell the user whether or not they've accomplished that level of SMI that was prescribed to them, and also be able to tell them whether or not it is time to perform an SMI again. Usually when prescribed an SMI, or prescribed a certain amount of SMIs from the doctor, it's usually 10 times in an hour. So our speaker and timer will, our microcontroller will alert the user through the timer and speaker every 5 to 10 minutes that it's time to perform it again. And all of these parts will be powered by a battery pack, which is also in the system. And we're currently thinking about using a watch battery for that as well. And in order to reset the whole system, we will have a reset button that's connected to the screen and also to the controller as well.
All right, so an additional mechanical aspect is the oscillating positive and expiratory pressure device, or OPEP device for short. This is used for exhalation therapy, which Omar will be talking about later. So for high-risk points, we have the OPEP and the valves. We feel that the valves and OPEP are high-risk points because the valves are what the air flows through. So there has to be complete accuracy and complete smoothness throughout the valves to not affect the flow rate. The OPEP device is important because we'll be designing this from scratch, meaning we have a lot of work to put in understanding OPEP therapy devices.
We've also been doing a lot of research on these topics, and we've also noticed that in our system, the most important connection that we have is between the diaphragm and the level sensor. And ultimately, the whole point of our system is to be able to record whether or not the user has successfully reached that volume that was prescribed by the doctor. And if that diaphragm does not reach the sensor, or if that sensor is not able to tell whether or not that diaphragm has gotten there, then our system won't work. So that's why this connection between the diaphragm and the level sensor is the most important, and what we will be working on probably the most in that project.
When creating our revised incentives barometer, we see these three themes as our primary critical paths. The first of those being the integration of electrical components with our mechanical parts within this barometer. The second of those being creating a valve to switch the airflow going into this barometer, closing that, and then sending it into the OPEP device. The third of those being creating a system to view recorded tests and successful installations. Now going more in depth on those three themes, the difficulty in the integration of the electrical components will be adjusting the sensor to properly work with the diaphragm, as the materials we choose to work with are going to hinder the sensor's performance, as most current barometers on the market are made using a plastic mold, and we don't have the ability to work with that. We have the ability to model via 3D printing, and currently we don't have access to clear 3D printing material, so that will be our first obstacle. And then the difficulty with the valve will be finding a way to, making sure that there is no air leakage into this barometer when the patient is attempting to use the OPEP device, because that will hinder how the OPEP device is supposed to function. And lastly, the difficulty with creating a system to record tests is we want to increase the interaction between the patient and the device, as our main issue, I've stated before, is that the patients often don't complete tests either by lying or just because they don't have incentive to do it. So creating potentially more interaction between the patient and the system will work in our favor. And in the next slide, we will look at potential plans on how to demonstrate our ability proximity sensor or a sensor of some sort to detect the diaphragm crossing the target. And our objective is to accurately record a successful inhalation trial. And to validate this, we will use a code output program. Our second requirement is to create a OPEP valve, and the objective here is to create a simple transition between the spirometer and the OPEP device. We will validate this through both simulation and experimentation. This validation method will demonstrate our ability to effectively switch between the spirometer and the OPEP device. Our third requirement will be to create an alarm system, and this alarm system shall have an adjustable audio reminder to for the patient to perform further inhalation therapies. But it should have an adjustable audio and visual reminder, potentially on an LCD screen, and this will be validated both through code output and again simulation. This demonstrates that the electronics can keep an internal timer. And again, this would hit our second critical feature, which is to remind the patient to complete their inhalation therapy.
So for the engineering analysis portion of our project, we need to do computational or mathematical analyses of our project to make sure that we can reduce the risk and any waste as we develop the product. One of the parts is SOLIDWORKS integrated flow simulations. SOLIDWORKS, as we will be modeling mostly in SOLIDWORKS, we can use their integrated flow systems to simulate air going in and going into the system and going out of the system. The valves are a central point as we need to regulate the flow of the air as the patient inhales and as he exhales. We need to make sure that our one-way valves that we will also model go correctly into the diaphragm versus the OPEP device. The air pressure as well is extremely important, and the simulations will give us feedback on that. We want the inhalation portion to be relatively effortless, as we need their breathing to be unobstructed for a more accurate reading of their breath volume. But for the exhalation portion, as it goes to the OPEP device, we need to make sure that the air resistance provided by the OPEP device is sufficient enough so that the patient can properly exercise their lungs as they exhale. Finally, the vents and outlets. We need to make sure that all this air going through the device is exited and distributed outside the device. We don't want the diaphragm to fill with air permanently, and we don't want the patient blowing into a dead end of the OPEP device, which will make it essentially useless. The information storage we can also simulate with computer code. There'll be a lot of trial and error, but we seek to have data viewing, data reset, and sensor interpretation. The viewing portion, we need to make sure doctors can at any point recover the data of tests that the patient has done. This will be stored in a memory cache somewhere on the device. It does not need to be very large, but since this is the analysis part, it's not really much of a work. But alongside that, of viewing it in storage, we need also to reset. We plan for the electronic components of the device to be detachable and reusable for another plastic housing. This will lower the cost of the overall device and make data acquisition and recovery a lot cheaper. As the device gets reused for each patient, the memory cache needs to be cleared. So we need to make sure that the function is built into the code so that it will reset only if it meets certain conditions. And finally, sensor interpretation. We need to be able to, the code needs to be able to take in data and interpret whether or not it is a real test that's a pass or fail, but also in the outlier case of a false test, something that the patient didn't mean to do, or accidentally turned the device over, which would give a false reading. We need to make sure that the sensor will be able to interpret data of pass versus fail, or even throw out the data if it meets certain criteria of being not quite right. And finally, you'll also be doing load analysis. Our electronic components will be consisting of microcontroller, LED, speaker, screen. All these different components will put a load on the system. Now there are a lot of specifications that are given with these components, and so using circuit analysis, we can examine what the draw and the power consumption of the overall system will be. That in turn, we compare with a battery sizing. Perhaps we need more voltage, and we can do a stack of buffer batteries. Or maybe we need a larger cell to last for the duration of time that we estimate the device's lifetime to be. Maybe a AAA over a buffer battery. This will all be calculated so that we can reduce waste in the project as we develop it and give a more reliable and accurate product. So in consideration of the riskiest parts of our project and the specifications that we have to meet, bringing all these considerations together, there's a proposed critical path.
You're good. Just keep going. We can just keep it running too, so it's, yeah, you're fine.
Keep it running. Okay. So in light of all the riskiest parts of our project and the specifications that we're required to meet in order for this project to be completely functional, there is a proposed way that we can reduce all these risks. The first and foremost one is that we're not going to be reinventing the device. We're going to be mainly relying on existing technology and designs for OPEP and incentives parameters. There are many well-documented research papers and thoroughly proven designs that are shown to be effective. We are seeking to combine and optimize all of these into a singular device. As you can see here, there are multiple different styles of OPEP devices, ones that involve ball bearings and others that go straight flow. We'll be looking into research papers to see which one of these will work best with our device, not only in terms of effectiveness, but also size and cost. Incentives parameters are a very well-proven device over the years and have been shown to be effective. So there'll be very little in terms of functional redesign that we'll be doing. While SB does not currently have the facilities to print a smooth plastic device, we will be doing simulations in SolidWorks, as can be seen here. SolidWorks has the ability to perform airflow simulations that will give us feedback on the pressure of our device, which will be an essential component as we investigate the OPEP aspect of the device.
So our incentives parameter 2.0 to correctly and accurately measure the level at which the diaphragm raises inside our spirometer. We're going to be testing different sensors. Right now, we are deciding whether to use proximity switches to determine the position of the diaphragm inside the spirometer, or maybe perhaps do a laser or a light sensor to where we can shine the light at the prescribed level where the patient needs to reach that target, and every time the diaphragm interrupts that light, we can record it. But that has also some challenges, because if we have a patient who's an overachiever and goes over this target, and then we record it as the diaphragm falls back down, we gotta figure out a way to mitigate the sensor or our program to not take that recording. That way we don't have double recording. So this is something that we have to figure out in our programming. We'll also be testing the different components for the battery load. That way we can determine the size for our battery capacity. The integration right now will be through a microcontroller. maybe a Raspberry Pi, since we have some folks here, myself included, we are kind of more comfortable using MicroPython or a Raspberry Pi 4, and that would help us write a better code to determine our sensor, and not only that, but to record it and also display it on an LCD display.
That all being said, I hope that we were able to inform you to the best of our abilities. But if you have any questions, go ahead and leave them in the comments down below. And don't forget to leave a like on the video too. And subscribe for all future updates from Team 8 Second Wind. Goodbye.